Okay, here's a quick video about how we should be able to recognize rational functions with removable discontinuities, right? So all these graphs are going to have holes in them somewhere. Okay, so there's one key thing that we'll notice here about how we can tell that your graph is going to have a hole. Okay, so let's do all of our things. So R is your roots. Okay, your roots come from your numerator, x squared minus 3x minus 4 equals 0. Okay, so this is where it crosses your x-axis. Hopefully, this is a factorable quadratic. I believe that it is a factorable quadratic. So we're going to do a quadratic style factorization. Okay? And we do that by answering the question, what numbers multiply to give us negative 4? And at the same time add to give negative 3. And the answers are negative 4 and positive 1. Okay, so those are the factors. Negative 4 times positive 1 is negative 4. And then we have a minus 4x from our inside, and we have a plus 1x from our outside, gives you a minus 3x in the middle. Okay, so it has to be able to multiply out to get you the quadratic that you started with. Now, to find the zeros, you set each of your factors equal to 0. So x minus 4 equals 0, x plus 1 equals 0. And we get x equals positive 4 and x equals negative 1. So we can go to your graph, since the whole entire point of these things is to get your graph on here. So we can put a positive 4 dot, and we can put a negative 1 dot. Right? Those are the two places, according to our equation, where the graph will cross the x-axis. Okay, R stands for roots. Where does it cross your x-axis? Okay, next we look at the vertical asymptotes. And the asymptotes come from where your denominator equals 0. So we do x plus 1 equals 0. And we see that x equals negative 1. Okay, and here is where the problem comes in. Right, if you notice on your graph, we have an intercept where there's an asymptote. Okay, which of course can't happen. We can't have an intercept where there's an asymptote. So this should tell us that there's something about our equation that we can simplify. So let's come back up here. We're going to factor everything once again. So remember this factor to x minus 4 and x plus 1. And in our denominator, we still have your x plus 1. So anytime we have the exact same parentheses in the numerator and the denominator, these can divide out, right? Anything divided by itself is 1. So basically, we're left with the equation x minus 4. So this is what we're going to use from here on out, is the equation x minus 4 to answer all of our questions. Because really, that's what we're graphing, with the exception of negative 1. Okay, so remember, we're just graphing x minus 1. That is a linear equation, right, with a slope of 1 that crosses your y-axis at negative 4. So let's keep that in mind here as we go through the rest of our steps. Okay, because the next step would be to do a table. But since there's no vertical asymptote, there's not a table necessary. So we can skip over the t part of making a table to figure out what's going around our asymptote, since there's not really an asymptote. Right? These guys basically cancel each other out as far as the graph goes. Okay, but we can go and do the E, right? The E stands for your horizontal asymptote, which, if it's a top-heavy function, we have an x squared on top and a x on the bottom. That means there's going to be no horizontal asymptote either. Okay, a top-heavy function is one that has a higher power in the numerator. So notice we have x squared in the numerator over just an x in the denominator, right? So the power on top is greater than the power on the bottom, so we're not going to have a horizontal asymptote. But we'll still have a y-intercept. So when we do the y-intercept, you basically plug in 0 for x. So 0 minus 4. Remember, I'm using the x minus 4 equation in order to figure everything out, so I get negative 4 as the y-intercept. So 1, 2, 3, 4 down, and we put a dot signifying the y-intercept. So we're going to finish this off by actually graphing it. We're graphing, remember, the line x minus 4. Okay, with one little exception. When it comes to your x equals negative 1 spot, we're going to put a hole there. Okay, so our graph looks exactly like y equals x minus 4. Has a positive 1 slope, has a negative 4 intercept, except for where we get to what used to be an asymptote, right? But we still have to have that there as our removable discontinuity. From your original equation, x cannot be negative 1, so when our graph crosses negative 1, we have to have a hole there. Okay, so that's the important part to remember about all of these removable discontinuities. That's what we have to remember about all of these removable discontinuity type functions. Whenever we can factor and simplify by dividing something on top and the bottom, that means our graph is going to have a hole in it at some point, right? A removable point discontinuity is what we called it before. Okay, so there we have one. If the denominator cancels out, then we have a line graph, right? A linear graph like we have there. But what about if the numerator cancels out? Let's look at that example. So here we have an example where it's bottom heavy, right? We have an x squared in the denominator and just an x in the numerator. Okay, so we should know already that there's going to be a horizontal asymptote at y equals 0, but let's run through our r, a, t, e, and y. So r are the roots. Where does this cross the x-axis? So we said x plus 3 equal to 0, and we get x equals negative 3 as your x-intercept. So you go to your graph, and we can plot negative 3 onto your graph. Okay, and then we come to the vertical asymptotes. So those are found by setting your denominator equal to 0. So once again, we have a quadratic that we can factor. What numbers multiply to give you 3 and add to give 4?
1, 3, and 1.
And those are x plus 1 and x plus 3. Okay, so those are the two factors, our two binomials that multiply together to give us that quadratic. So if we set each of your factors equal to 0, we get to have a vertical asymptote at negative 1, and we have a vertical asymptote at negative 3. So once again, here we're going to run into this novel situation where we have an intercept and an asymptote at the same place. Okay, so we have an intercept at negative 3, we have an asymptote at negative 3, and this, once again, can't happen. So that's going to lead us to come back up to our equation and factor it. Okay, so the top doesn't change, just x plus 3. And the bottom we said factored to x plus 1 and x plus 3. So we can divide x plus 3 by x plus 3 and get the basic equation 1 over x plus 1. So this is going to be our rational equation that we end up graphing. With one exception, it's going to have a hole at negative 3. So where the graph crosses negative 3, we are going to have a hole. Okay, so then t, we only have to worry about one vertical asymptote, right? That happens at negative 1. So we make our table to see what's happening around negative 1. So we have negative 1.1 on the left and negative 0.9 on the right. And we're going to use this green equation to decide whether we have a positive value or a negative value. 1 over negative 1.1 plus 1 is 1 over negative 0.1, which is negative 10. So on the left side of -1, our graph is going to be pointing down, right? Going down towards negative infinity. A -10 means our graph goes down. And similarly, we're going to do it for the right side. -0.9 plus 1, which is 1 over positive 0.1, which is a positive 10. So on the right side of your -1 asymptote, our graph will be going up. So T stands for table. We want to see what is the asymptotic behavior around your asymptote. In this case, our only asymptote is -1. We don't worry about -3 because that's the one that's not really an asymptote for our graph. Okay, E would be the horizontal asymptote. Because this is a bottom-heavy graph, we have automatically y equals 0 as the horizontal asymptote. Every bottom-heavy graph has y equals 0 as its horizontal asymptote. And then y, where does it cross the y-axis? So 1 over 0 plus 1. Remember, I'm using my green equation. 1 over 0 plus 1 is 1. So we'll cross the y-axis at 1. So let's see what our graph looks like. To the right of our asymptote, it comes down, hits +1, and then heads off towards 0 to the right. Okay, so nothing changes on the right side of our asymptote. It's the left side that's the interesting part, because as we come up like this and we approach -3, we have to have a circle there, right? We have a circle representing the fact that your y value does not exist when x equals -3. So we have a hole right in there. Now, if you have a pencil or something and you have enough space, you can erase that little vertical asymptote dot in there to make it look something like that. Okay, so those are our two different types. If you have the the denominator cancels out, like in example 1, you have a line graph with a hole in it. And if, like example 2, your numerator cancels out, you're going to have your rational graph, your standard rational graph with a hole in it somewhere also. Okay, so that's how we can tell that we have a removable discontinuity or our graph is going to have a hole somewhere.